This video is going to introduce us to area and then also look at a couple of different propositions that deal with area and proofwriting as relates to area. So the first thing is talking about area, and Euclid doesn't actually use the term area. He instead uses the term equal content, and they're not exactly the same. Area and equal content are not exactly the same, but they are close enough that anytime you see those buzzwords equal content, just go ahead and think of them as area in your head. Okay? So first of all, some properties. And the properties that we worry about with equal content or area are the following. If you have two congruent figures, or as many congruent figures as you want, they should all have equal content. In other words, they should all have the same area. This notion of equal content is transitive. In other words, area is transitive. And what that means is if you have the area of figure 1, and that area is equal to the area of figure 2, and suppose you also have that the area of that same figure 1, and I'm going to abbreviate here just as figure, is equal to the area of some other figure, let's say figure 3. See, I'm being super lazy with my naming conventions. Then the conclusion that you can get to here is that the area of all three of those figures is the same. In other words, you'll get that the area of figure 2 and figure 3 are also equal. Okay, and that's all we might mean by transitive. In other words, you can apply your common notion number 1. The other thing that you can do with area is you can add or subtract this equal content. So note, what would this mean in terms of adding and subtracting area? You've totally done this in your past. If you needed to find the area of this figure right here, what would you do? You'd take the area of that four-sided figure and you'd add it to the area of your triangle. So this would be adding area. Now what would you want to do if you subtracted area? And you guys have totally done this before. Think especially in recent years, it probably would have been maybe a Calc 2 class where they do those washer things all the time with area and volume. But here, just to give an example, suppose you had some four-sided figure and it had a hole in the middle, and the hole in the middle was another four-sided figure. In this case, if you wanted the area of the shaded region, you would take the entire area and you would subtract the area from the middle. Okay? So that would be the notion of adding or subtracting area, and this is something we do all the time with area. And this is what I said a little bit ago. Note, equal content is roughly the same as area. In terms of notation, and this is why I was being very careful not to write anything down in symbols just a second ago, but the notation for area is this lowercase alpha, the Greek letter A for area, and it looks like a function notation where the thing inside the parentheses is the figure that you care about. So if that's a triangle, you'd put the symbols for a triangle there. If it's a square, you'd put the name of the square inside of the parentheses. And we'll see that here in just a second. Alright, so let us look at an example. And the example that I want to look at is Proposition 35 in Book 1. Proposition 35 in Book 1 isn't one we've gone over before, but it's right after one we have gone over before. A reminder, Proposition 34 in Book 1 was almost everything you could want about parallelograms. Remember, it gave you things where opposite sides, opposite angles of parallelograms are congruent to each other, and you could cut a parallelogram in half and either side would have the same area. Okay. Since this is right after that proposition and also talking about parallelograms, note, logically speaking, this is a proposition we should put on a scratch piece of paper that says, hey, we might use it here. Alright, so let us look context-wise what we're seeing here. So we're going to start off and we're going to be given two parallelograms. I went ahead and already named them, A, B, C, and D, and E, B, C, and F. We're told that the two lines AF and BC are parallel. And what we want to do is we want to show that the area of these two parallelograms are equal. Now notice something here about naming convention. It is common when you name polygons, whatever letters you use to name your polygons, that you'll actually go around the polygon either clockwise or counterclockwise. Different people have different standards. Your book does something that is very non-standard, which your author sort of goes in stripes. So I try to most of the time go around either clockwise or counterclockwise, which is the standard for you guys, but every so often I'll match what your book does, especially in a tricky area. That way you guys don't see conflicting symbolic use. So parallelogram ABC. D is A, B, C, D. Notice it's parallelogram, so AB here, opposite CD, AD, BC opposite. The other parallelogram is EBCF, and notice BC, those two guys are next to each other and in both the parallelograms. This is telling you that they are going to be sharing a side right down there. Notice also the AF, that went ahead and collected both of the two non-shared and sides of the parallelogram, specifically the two sides that were opposite the shared side here. Okay, so that's just naming convention. So down here, when we actually start looking at the proof, just like the last couple of examples that we've done out of this section, I went ahead and put the givens outside of the T-chart. That is not something that you need to do. Go ahead and put this as the first line of your T-chart. I did it just so that the picture wouldn't be all on top of our T-chart. Okay. So went ahead and highlighted the two parallelograms that we have, the orange parallelogram and the green parallelogram. Orange being ABCD and green being EBCF. Okay, just try to make that easier for you guys to spot them. Okay, so we put this in our T-chart, and the very first thing that I am going to claim is I'm going to claim that if we look up in this parallelogram ABCD, and this here is I was just referencing which parallelogram we're in to make it easier for us. So in this orange parallelogram, AD is congruent to BC, AB is congruent to DC. In other words, opposite sides of your parallelogram are congruent, and this is totally just applying our proposition 34 to ABCD being a parallelogram. Now notice what you can do. As soon as you do that to one parallelogram, you can go ahead and do it to the other parallelogram. So let me go ahead and write down the information for the other parallelogram. So we've got EF is congruent to BC, and remember what we already had. EF congruent to BC, and the new thing we get is that EB, 1, 2, 3, is congruent to FC. Okay, so there are hatch marks to indicate who's congruent to who. And I went ahead and put in the hatch marks back from the first parallelogram because seeing all of those hatch marks in your picture right now makes it really obvious that what is going on. So I'm going to take a second to pause here. You guys think about what information can we immediately grab from this, and it turns out there's a lot. Alright, so coming back just to the sides, we can immediately say, hey, well, just with these symbols, we know that AD has to be congruent to EF, and of course, that is because that they are both congruent to that shared side BC. Okay, so we're going to get that for free. We're also going to use the fact that we've got two parallel lines here up at AF, same line as long as you do the full line, and BC are parallel, which means we've got going to get a lot of angles that are congruent as well if we use alternate interior angles or corresponding angles. Yeah. I went ahead and grabbed the sides first. So here AD congruent to EF, specifically using our logical glue of common notion number 1. Now, I'm also going to claim that DE is congruent to itself. So here's DE. Okay. Now, may not notice why yet, but it'll be apparent in just a second. And the reason why, actually, let me just go ahead and tell you. The reason why here is we're going to start looking at adding lines. Specifically, I don't care about the line segment AD. I want to know about the line segment AE. Similarly, I don't care about the line segment EF. I care a lot about the line segment DF. Okay. Now think about it for a second. What do we know about those two line segments? And hopefully you're all thinking that those two longer line segments are just the two congruent line segments plus that same little piece. Okay. And it turns out, yes, that is correct. So this is specifically adding in that same little piece of DE onto the already congruent line segments, which is exactly what common notion number 2 tells us to do. Now, why do we care about that? We care about that because we're actually going to be looking at these two triangles. So that triangle and then this triangle right over here. And what I'm going to claim is I'm going to claim that those two triangles are in fact congruent to each other, and they should highlight here in just a second. Nope, they didn't. Okay, so I'm going to claim that these two triangles are in fact congruent to each other by side angle side. There's a lot of different ways you can do it. You can also do this by side angle side. And what we have is the two longer sides are congruent to each other. We could also have found that these two angles are congruent, but instead went ahead and said, hey, we know from previously that AB is congruent to DC. And we also know that, where'd the other one go? BE is congruent to CF. Okay. Notice that takes care of all three of the sides of those two large triangles that are across the top of our two parallelograms, plus a little bit more. And this tells us, hey, that those two triangles are then congruent to each other. Now we're going to use this in order to build to the area of the two triangles. Area of the two parallelograms. Unfortunately, the area of the parallelograms is not exactly the same as this triangle, so we'll build up. But one of the things that we know is, once we know that the triangles are congruent, we've got that their areas are congruent, and this is a natural thing with area. It's the same idea of if you say that two angles are congruent, their measures or their degrees have to be the same. All right. So there's the stuff that we just did. Now, let's put this all together. I am going to claim the following. I am going to claim that if we look at the parallelogram ABCD, this is the orange one, this is exactly the triangle EAB, so the big triangle right up here. Subtract out the little shaded triangle that I'm shading in right now, and adding back in this other triangle that is triangle BGC. Okay, so notice we took the big triangle we just looked at from a congruent standpoint. We subtracted out the little bit that was outside the parallelogram and added in the part that the big triangle didn't cover. Okay, so this here is true just by pieces that coincide with each other are going to be congruent. Okay, I went ahead and phrased this in terms of the area just because most people like to think of it that way more. Okay, now what do we know? We know that we can actually do something very similar with this other parallelogram. This other parallelogram right over here, that's the green shaded parallelogram, also has a big triangle. We're going to delete out the shaded in part of the teeny tiny overlap, and we're going to add in the vertical stripe shading triangle at the bottom. Okay, so I'm going to do this in stages. I'm going to claim, actually I just went ahead and did the exact same thing. So this is the big triangle FDC. Get rid of the tiny overlap guy that I just shaded in dark, and then add in the extra missing bits down there at the end. And same reason as before, because we did the exact same thing. Notice there's only one change between these two guys. It's that original huge triangle at the top, but we already know that those two areas are exactly the same, so I'm just going to replace. Okay, so this here is just saying that same thing. It says, hey, take the same part that we had right up here, replace that original triangle with the new triangle we care about, and it's still identically the same, and this was just a little bit of algebra. Now we already know that this first part is the same as the area of parallelogram ABCD. The second expression is the same as the area of parallelogram EBCF, which means we can go ahead and get to the conclusion that the area of the two parallelograms is exactly the same. Notice you could also rewrite these algebra steps in slightly different ways. In either case, you're doing some adding up the pieces of the area to get the area you want for each parallelogram and showing that the two of them are actually the same. The big key step right here is that guy right there, which is the triangle EAB and the triangle FDC being congruent to each other or having the same area. And that's actually a really, really useful guy in terms of parallelograms, saying, hey, if your parallelograms live between the same two parallels and they share a base, the area is exactly the same. It actually gets you into where you develop the formula for the area of a parallelogram too. And it turns out right after this, so this is two propositions later in Euclid's first book, you have almost exactly the same result, but for triangles. So this one here says you've got two triangles that lie between the same two parallel lines. If they share a base, so share the base right here, then they're going to have equal content, or they're going to have exactly the same area. Notice what this is telling you. By sharing a base, that means the length of their base of the triangle is exactly the same. And by lying between the same two parallels, this in fact tells you that in modern speak, they have the exact same height. This is somebody that we will use quite a bit. Okay. I'm not going to go through the proof of this one, but if you are interested in the proof of this one, what you do is you build up to two parallelograms, so the new parallelogram that is formed with those extra lines. You'll then get, because these two parallelograms are between the same two parallel lines, that the two parallelograms have the same area, and then the original line of the triangle right here actually cuts these parallelograms in half by proposition 34, and if you have two areas of the parallelograms the same, if you cut that area in half, the new halved area is still the same, so the area of the triangles are the same. So this one here is a really straightforward proof if you pull that area of the parallelograms being the same that we just completed.